Good afternoon, everyone, and welcome to Day 2 of the 2026 Human Leader Challenge Forum. We have our last presentation of the day and of the entire forum with California Polytechnic State University, San Luis Obispo, and PHAT, Peltier-based Hydration Accumulation Terminal.
Thank you so much for the introduction. Good afternoon, HuLC competitors and HuLC judges. I hope you guys enjoyed lunch. We are PHAT.
PHAT stands for Peltier-based Hydration Accumulation Terminal. I'd like to make some introductions. I'm Tarsem.
I'm Ethan. I'm one of the co-leads with Tarsem.
I'm the co-lead.
I'm Taehoon, I'm the treasurer.
I'm Renee, I'm the project manager.
And with us today is also our advisor, Dr. John Chen. And not with us is our coach, Rick Lasko.
First, I'm going to start off with the challenge. Currently, NASA potable water dispensers allow increments of 250 milliliters to dispense hot and ambient water. The figure on the right shows the ISS potable water dispenser that includes an ambient water cycle and a hot water cycle that flows through the heater. Our goal is to provide water by building upon this design and further assisting with crew member hydration and food rehydration. To do this, we have 6 objectives and constraints. We want less than 16 degrees Celsius water temperature at the outlet. We want to preserve the original heritage while also adding our cold water system. We don't want any refrigerants or moving parts. We want our design to fit within a NASA Express Rack configuration. We want our design to be operational for a 30-day lunar mission and 1,200-day Mars mission, and we want our design to be maintainable and modular as well.
So here's our PHAT impact. So for the mission impact, our project has its own meaning. It's the first time incorporating the new cooling system into the existing potable water dispenser. So we are laying the fundamental baseline for the future expansion, improvements, and mitigation for the cooling water system. Our system's heritage is based on the already flight-proven ISS potable water dispenser system, which is rated TRL9. So that gives us lower risk, higher reliability, and resilience. The whole water dispenser system, including our new suggested cooling water system, is designed to fit in the rack scale, meaning the physical integration of our system into the spacecraft is reasonable. So most importantly, the reasonings for choosing the Peltier cooling modules over the typical vapor compression cycle include, first, our system is solid state, meaning it has no moving parts, and that gives us extra stability. Secondly, it uses no compressor, so there is no issue regarding the vibration and the noise the compressor makes. Also, our system does not utilize the refrigerant gas, meaning there's no refrigerant gas leakage issue, and that ensures the crew member safety. And last but not least, since we are because we are heritaging the existing potable water dispenser system, even if the cooling system fails under the extreme case, the remaining heating system and the ambient water system will continue in operation. So even the cooling doesn't work, these 2 remaining systems are capable of continuing their original missions.
So to go over the architecture to begin with, we start with our heritage features, including the bus interface, which is present on the ISS module, as we found in a paper from 2008, as well as the dispensing needle and the switch to put the package in place and clamp it down, as well as a manual valve. We chose not to use any digital interfaces as like any any damage could possibly fail the cause complete mission failure if not able to be repaired. And we also added the auxiliary output as well in case, for some reason, the existing microbial filtration or other dispense features all fail and the astronauts possibly have to drink iodinated water as an emergency. And to visualize the different loops, we have the ambient modes, which is the same as the ISS, as well as the hot mode, which features the same concentric coil heater system, which is present in the ISS. We chose to keep this system because it solves the existing issue of bubbles forming on the outsides of the pipeline, which inhibits heat transfer and requires more power. And then our main staple is the cooling loop, which is highlighted in green, where we have a new solenoid valve going through a tech array of 10 thermoelectric coolers in series going out to the outlet. And as you can see in the outlet, we have a UVC filtration system at the very end as a last step, kill step for the whole process. And this is a visualization of what the pipeline will look like. We have the 316L steel, a copper saddle block, and a Peltier cooler on top. And on top of this would be a heat sink of some sort that we will get to in the next couple slides. And as Taehoon said, the hot and ambient path is unchanged, and the Peltier system is independent. We learned that the Peltier cooling system is more of an amenity than like a survivability feature. So we figured that we would try to prioritize survivability so that if the Peltier system fails, the astronauts can still survive and reheat their food and stay hydrated.
So for our piping, we at first wanted to use copper due to its advantageous thermal conductivity. However, since copper is reactive with iodine, we unfortunately had to resort to 316L stainless steel, which has a fraction of the thermal conductivity. This means that we're going to have to use more power for heating and cooling, but we worked to mitigate this by using the copper saddle blocks, as we saw before, which are going to be mounted to the outside of the pipe, where the Peltier cooler will mesh there with some sort of thermal interface material to further increase the conductivity between those surfaces. And that should work to mitigate some of the shortcomings of 316L when it comes to thermal conductivity.
And as you can see with our simulation, we ran a MATLAB script where you can change the number of modules, the conductivities, the size of the copper block, and we found that with 10 modules, the water does reduce from the worst case scenario of 27 degrees Celsius to about 16 with 7.4 amps of power. And this is with assuming that we use 15 amp weighted tech modules. And another thing with thermoelectric coolers is the coefficient of performance is much higher at lower currents. So by overscaling or overspeccing the techs, we're able to harness more efficiency from them. And on top of that, if any sort of issues arise, such as degradation in thermal conductivity and whatnot, we could just increase the power to bring it down. And as you can see, for the better cases, it goes well below 16 Celsius. And for the module count trade, we ran the same study, but with multiple modules above and below 10, and we found 10 to be the sweet spot, as adding in more can affect the geometry. And with less modules, it had to draw more power per module. So this is like the sweet spot we came up with. As you can see, the curve slightly smoother and flatter, and the power only drops only about a couple hundred watts. And after all this, it's still under the 2,000 watt budget of the current ISS Express rack and whatnot. And as you can see, the results are all shown here. Best case scenario is about a COP of 7, and then the worst case is a COP of 0.9, which is to be expected from Peltier coolers. And as you can see, we are able to reach our limits with just Peltier coolers.
The total envelope of our system, as we've said, is designed to fit within the express rack locker. And we've estimated our system's mass to be 30 kilograms. This is a bit of a conservative estimate based off of cataloged parts and masses. And this is also estimated with the 14 kilograms of that coming from the cold loop that we've added, and the rest being based off of an estimate of how much the heritage core weighs, being 16 kilograms. So as we can do some little math there, we see that that's a roughly 100% increase in the mass. And since this is a conservative estimate, it is likely that this will need to be refined. And we could do that by shaving down some of the mass in the solid heat exchanger blocks that we saw earlier, make those as small as possible, as light as possible, as well as optimizing the pipe geometry to save on pipe length and additional mass, as well as like structural supports and things, which we can use to shave it down.
So here's the brief bench test we conducted. The primary purpose of our bench testing was to validate that our flow-through water loop system does work under the integrated Peltier cooling system. Also, we tried to measure the temperature difference between the inlet and outlet, the flow rate, and the required power input. So as a result, we achieved the 2 degrees Celsius decrease in temperature from the ambient water temperature of 25 degrees Celsius to 23 degrees Celsius. We found 3 main obstacles that we need to deal with. First, the residence time was too short, meaning how long the water is in contact with the core side of the Peltier cooler to get cooled down was too short. Secondly, the hot side heat rejection was too inefficient, as can be seen from the pictures. It's using the fan-based air cooling system, and that had too high thermal resistance and was too inefficient. And lastly, there was a heat gain through the uninsulated tubes, so we also had to deal with the insulation issue. And quick side note, there was a small typo on the slide, so we made a quick small modifications in the morning.
This was our verification prototype that we made as part of the Cal Poly Senior Project process. It's essentially a PHAT Junior. It's the same fleshed out system, but simplified. It only has 2 tech modules, and it lacks filtration because we deem that too expensive and already proven to work. And we did not include the flush system because we deemed that unnecessary for our verification. So with our verification prototype here, we were able to achieve a temperature drop from 2 ounces of water to get from 22 degrees Celsius to 16 degrees Celsius, which is within spec of what we are looking for. And that just took 60 seconds with 2 modules. So this verification prototype did its job, and it verified that our Peltier-based cooling was sufficient if scaled up to what NASA would require. Yeah.
And as Taehoon said, we had these lessons learned from our physical prototype. So part of that includes the flow rate, which is a big issue as shorter residence time will not be sufficient enough to cool down the water. So we reduced it to about 40x, which is actually convenient because it fits the half a liter per minute flow speed that was presented in the 2008 paper on the ISS water dispenser. And for the hot side rejection, fans were not enough, air cooling was not enough, so we chose to opt for heat exchangers, and that is an open item on our next steps. And for our insulated lines, we chose a 60 millimeter aerogel enclosure, which was sized based off the dew point and the outside temperature regulated for the inside of the Peltier cooler. And for condensation protection, we have to note that with these coolers, the physical cold side of the Peltier cooler, at the worst case, does reach around 1.8 Celsius, which is above freezing. But that is a bit too close for us, so we need to figure out how to mitigate that through some sort of feedback loop, like some current control on the Peltier coolers. Possibly adding more might reduce this more, will reduce the current overall. But like we said previously, the geometry is a factor when it comes to this. And for condensation, like I said earlier, we're going to stick with aerogel, as it's been proven to be a very good insulator for this process.
The cost of this project, we calculated using NASA's PCEC software. And we used a multivariable CER, taking into account the first pound cost as well as the analogous systems that already exist. And we did this using an assumption of 2 units over a 10-year period, one for the lunar mission, one for a Martian mission. And from this, we found that the total PHAT project budget was $9.2 million. And for reference, we also ran the same CER, but with the mass of the ISS PWD, so as if they were reinventing the same exact device to send out, just for a comparison on the project cost. So the total cost roughly doubled, with the production cost being of 1 unit of PHAT being $1.3 million, and for the new ISS PWD being $550,000. So this cost increase is something worth considering, and that goes hand in hand with the mass estimate that we got. If we shave down the mass, we shave down the project cost. But again, this is a very conservative estimate, and it has refinement that can be made to get a more accurate cost. For the technology readiness of this project, as we know, the ISS PWD has a TRL of 9, as it's currently orbiting above us or below us. So this has a TRL of 9, and since our system is highly based off of this, that gives us a bit of a leg up. Thermoelectric cooler modules, they have been used in space for instrumentation cooling, but not for water cooling in space, but they have been used for water cooling here on Earth. So we gave that a technology readiness level of 6 or 7 between those two. And the materials that we chose for our PHAT system, we gave a technology readiness level of 3 due to the fact that we have proven them in the proof of concept. However, they still need more development as a complete system. So overall, we give PHAT a level 3 TRL due to the nature of the work that still needs to be done. However, due to the heritage model that we approached this project from, it is likely that it would accelerate through the TRL levels quicker than otherwise due to the familiarity with all the concepts here. So looking forward, by the end of 2027, we'd probably reach TRL 5 by having all these components tested individually, and then by 2029, as a whole subsystem, we'd reach TRL 6. Then by 2032, we would be able to have that system tested in space, likely on the ISS, to reach TRL 7, and then 2033 and onward, we would reach TRL 8 and 9 by getting certified for HLS and then actually going on the missions. So that's what's ahead for PHAT. Talking more about those missions, for the 30-day lunar mission, we would not get anywhere close to the lifespan of the thermoelectric modules, as we estimate they would take 15,000 cycles in order to fail on average. And that is a conservative assumption, of course. And over the 30-day lunar mission, we only expect to see 240 use cycles. So the only maintenance that would need to be done in that case would likely be due to catastrophic PHAT failure. And so no additional parts would need to be brought on except in case of redundancy. For the longer 1,200-day Mars mission, however, with 9,600 tech cycles, that gets within 50% of the expected lifespan of 15,000, sorry. And with 10 modules, it is possible that one or more would fail due to the statistical distribution there. So in that case, it would be wise to have the crew prepare for replacement by bringing extra modules and training them how to replace it. It would be easy as disconnecting the old one, reapplying thermal paste, wiring it back up. Another advantage of our system is that in the case where one or more does fail, the entire system is still functional, just you lose some cooling performance. And so it's not necessary. Cold water is a luxury here. We'd like to give it to them as much as possible. However, if it fails, they will survive. And so that's our elegant solution there, PHAT. Thank you.
And thank you so much, Cal Poly PHAT team. We'll move on into the Q&A session now, beginning with Zach.
All right, wonderful. Thank you for the name. I appreciate it. It's
my pleasure.
Makes me feel like I'm in high school again. Good stuff. Okay. So the power draw, does it only draw power while it's dispensing water, or is it are those modules constantly running?
It does not passively use power. It turns on for a bit while it's warming up or cooling down, and then once it's finished with its dispensing, then it powers back down to roughly 0 watts.
Okay, so it's just during that
yes.
phase. Okay, thank you.
Mm-hmm.
All right, you may have kind of answered this question at the end. So when your Peltier elements fail, you're just going to assume, well, you can live without cold water. Can it operate losing 1 or 2 or 3 Peltier elements and keep operating? And how easily can one of those be replaced?
Absolutely, yeah. So since we have 10 modules, that's plenty, and since we're running them at half current, the other ones can also be bumped up in current to get similar cooling values. But yeah, even if one fails, the rest will be fine. Go ahead.
I'll make it very clear. Well, we can increase the current, and we did test it with the current, at the degradation of the thermal resistance being higher, like the current going up to 8 amps instead of 7. If you keep going up, you'll introduce thermal fouling, where it's the power is I squared times R, I think. What happens is the Peltier cooler will end up getting warm from just the electrical current. So that is one issue that we also have to mitigate with current control. So while, yes, it can run with some modules failing, there's a hard limit where if it reaches possibly 11 amps or 12 amps, it could end up just warming up the water instead. So we would just suggest replacing them immediately, as soon as possible.
So I can replace 1 or 2 of the elements, or do I have to replace the whole set?
Just a couple elements, the ones that aren't working. So we'd have to have some sort of diagnostic tool to make sure that the astronauts are able to tell which ones are not working up to par.
So I guess in the first part of your presentation, you mentioned that the heat from the Peltier coolers will go through the cooling loop.
Yes.
Right? Why not just use the cooling loop to cool the water? Wouldn't it be the same wattage? I'm just asking. I don't know. I didn't do the calculations.
Wait, I'm sorry.
Why not use the cooling loop with a heat exchanger instead of having a Peltier cooler in between? Did you do any work related to
no, because we figured that heat exchangers are more they would draw heat away, but they don't necessarily draw heat from ambient water, like a heat pump or a traditional refrigeration cycle or a Peltier cooling system would. But we didn't quite consider fully if we just use a heat exchanger on a pipe to draw heat away from water.
Great presentation. So, quick question is regarding the how things work. So basically, you attaching the saddle to the piping, right? How do you make sure they can survive the launch load?
That's a great question, and that's one that we definitely have more work to consider. But for starters, sort of locking clamps on is what we were envisioning at first. We would need to do some more analysis to figure out, if those would survive. But additionally, like a quadrilateral screw-based bracket is another thing we puzzled around. But we haven't determined an exact solution to that. But that is something we have been considering.
Since there's no reservoir like on the hot side, what's the line length between your cooling and the dispenser, and what do you anticipate crew should do or would do with the water that is dispensed before it's cool?
That's a great question. So yeah, since we don't have reservoirs and it's a flow-through system, that is one challenge, is we don't want water sitting stale in the pipes. The length of the tube is at most
About 1.5 meters.
1.5 meters. Not straight, but 1.5 meters total length. And so that could, that amount of water could add up. We considered a few options. Obviously there's the flush system that already exists in the ISS PWD, and we do wish to incorporate that as part of our system. However, like having to flush it every use is kind of inconvenient. In the end, we kind of settled on a little bit of a non-solution solution, which is that the expected use case of the PHAT system is that it would be used frequently enough where the water in that leg would not have time to rot away, really. And then we also have the UVC filter on the outlet, so any accumulation that could happen in the 4 hours that we kind of expect between uses would be sterilized on the way out.
Well, that's great for microbial control, but what about temperature?
Another great question, yes. I don't think we actually considered that, because
Especially with a 1 meter line length, that's going to
Yeah.
warm up really fast, and nobody's going to want warm when they ask for
Absolutely.
cold.
Yeah, I think definitely, the insulation will help, but it will still warm up in that 4-hour timeline. So that's something we'll have to think about. We could just, move the outlet closer. We'd have to puzzle that out a little bit, but that's a great point. Thank you.
Yeah, I think a lot of that come out with flat packaging for a lot of these projects. And similar to all the other potable water dispenser projects that we've heard about this past 2 days, yeah, I think there's a lot of similar comments across dead legs, thermal transients, right at the needle when they're going to go to dispense.
Right.
You don't want the last guy's hot tea water coming to your cold sports drink. But so I'm hoping all the teams are listening to all the comments that are coming in, just considering those as a big picture item. One question specifically for yours. You said you flowed the water down at 40 times slower, something like that, to get more efficiency. Or is it 40 times the efficiency? I'm sorry, I didn't.
Was it at the end or the beginning?
Near the testing.
Oh, yeah.
Emissions. Yeah.
Yeah, so originally in our testing, we had a pump, we pumped it by hand, and it was too fast, so we sort of just lifted up we got an aquarium pump, we sort of lifted it up to make it more, we lowered it down so it'd have to use more head, and we throttled it down, and that got us the temperature drop that we needed.
Okay, so whatever you were flowing was way too fast
Yes.
for what you needed.
Yes.
So my original question was going to be, do you expect to see a 40 times decrease in your dispense rate if you slow down at your cooling side? Because
Right.
you don't want to wait 10 minutes for your sports drink.
Yes, of course. So the 40X was sort of the number we got from our testing, our initial bench test to our verification prototype. But our calculations for the actual fleshed out PHAT design are using a 0.5 liter per minute dispense rate. So relatively quick, and you can get a cup in just a minute.
Okay.
Yeah.
I think that answers it.
Okay.
I saw that number there, and it triggered a crew usability
Yeah.
concern.
It's a big number. Thank you.
Thanks for the presentation. I really enjoyed that y'all included details on your test setup, and the meatball logo etched onto your test was appreciated, didn't go unnoticed. So do you guys have any plans for incorporating temperature selectability or dosing selection functionalities?
That's a great question. So on the premium NASA edition, we will have the same sort of knob for the 250 milliliter increments. We didn't incorporate that here. However, we did puzzle out whether or not we should include like a smart temperature control with mixing. However, we settled on having like 3 discrete levels to minimize controls, to minimize computation, to minimize system complexity. So,
Can I add something to that?
yeah, feel free.
Yeah. So, one thing to answer your question as well, and to follow up with other details, is this could be expanded upon for like this idea could be expanded on besides human landers if it's if you have more space, and if we're able to improve the efficiency. We could probably run and maybe improve the space allocation. We can probably include more Peltier coolers. And as you can see with the graph, we have about, we're at around 2.5 degrees Celsius for the best case scenario. And that could possibly, like, we can bring the worst case scenario down to as increase the amperage depending. And if we incorporate some sort of feedback loop that's precise enough, we could just say, hey, the inlet temperature is like 18 degrees Celsius, and I want water that's 11 degrees Celsius for my maybe a space milkshake or something, or whatever you want, right? A water shake. Well, so that would be like the future plan. If this idea is like tested, like works just for cold drinking water, and then refined after that, we can try to include some control.
All right. Thank you.
Let's see. I don't recall saying anything on overall project risk tracking. Have you considered that, and maybe what some of your top risks are?
Yes. So that is a key thing that was in a senior project curriculum for school as well. We knew that refrigeration was more efficient, but our group, like all 6 of us, agreed that the risks with refrigeration was too high, like such as like pressure drops for the condenser and the compressor, refrigerant leak, as well as moving parts and maintenance. And we figured that because the Peltier module is solid state, the risk is little to none. The only risk could possibly be like burns if the astronaut is not aware of that a Peltier is hot while maintaining it, which is a question that I forgot which one of you asked with the other team about replacing modules. But that would be, so for risks, it would be burns, and there's no chance of leakage, and all the parts are all like solid. So it would be very minimal risk in terms of like danger to the astronauts.
If I may add, yeah, this slide here we have on freezing condensation. Those are 2 other concerns. We don't want condensation and loose water in the capsule, so that is another big risk. That's like our main risk in terms of like the machine rather than the human risk to being burned. So our big like risks in terms of the device are freezing and condensation, and so that's what our insulation solution is what we'd like there.
Okay, thank you.
Thank you.
So I'm going to poke a little more. It looks like your Peltier elements, you flow through them and attach the water lines to it, or the Peltier. Okay, so you heard us talk about QDs before. How are your connections done such that your modular and you see you can replace the Peltier elements? How am I safely connecting my water lines such that I can do that in such a compact space?
Yes. So let me just say, these were merely the ones that we got for our senior project. They were very cheap, and that's why we picked them.
I figured as much, but I'm still curious what your plan is for a.
So for the actual for the premium PHAT, like we said, we want to have the saddle block format. So this is the solid state device right here, that white plate, and that would be flush against this copper plate, which envelops the copper pipe. So there wouldn't be the flow through, the water block kind of architecture. It could end up that would be more advantageous, but for now we went with the enveloping kind of structure, and so there wouldn't be any pipe fittings needed to be.
So how are you attached then, so you can get it off of the?
Yeah, and that's what Leon was asking earlier. It was a great question about fixturing to resist the launch loads. And so, yeah, right now our kind of preemptive kind of solution is either corner screws but those are prone to vibration. But luckily, our system doesn't vibrate because it's in solid state, or some sort of locking clamp.
So you're using copper and stainless, right? So material selection. I had to look it up because I forgot. How are you going to mitigate corrosion, galvanic corrosion, and other stuff?
That's another great point. We did not consider the effect of having the two dissimilar metals touching as a vector for galvanic corrosion. I would say I know there's methodologies that we use when there's dissimilar metals, like a sacrificial anode. That might be a little bit inappropriate for a space mission, but that is a good consideration that we had not actually thought about. So thank you for pointing that out.
I want to pick on the analysis portion. Can you go back to the temperature like which you utilize to determine 10 of the modules? The last one.
The one before that?
Yeah, that one. So based on your Reynolds number, it's 471. So it's a nominal flow, right?
Yeah.
For nominal flow, it doesn't mix. Then basically all the water touch the wall will be cool to 16 degrees Celsius. But in the center of the pipe, it's not going to be 16. And your pipe length is about 0.5 meters, which is not long enough for the conduction to happen to reach to the temperature you want. So does it mean you need to have one additional module as a redundancy, just consideration of the fluid properties?
Yeah, so we would likely have to consider the study, but we just picked 10, but what you're saying is correct. That's why we did a sweep of multiple modules to see how feasible it is. But you're correct. We also did consider increasing the Reynolds number, but then that would increase the flow rate, and that would decrease residence time. So that's another challenge. One thing I did think of was possibly changing the pipe geometry, but then that would have pressure issues in the long run as well. Because if we can change the pipe geometry to a flat side, it would have more contact, possibly eliminating the copper block entirely as well. So one thing I would think, one solution I thought of was how to agitate the water, but inside the pipe. But then that would create pockets possibly for microbial growth as well.
Right, because right now you don't have a mixture, and that's causing the problem. Okay, thanks.
One thing I'd like to add to that is another more primitive solution that we considered is running the coolers to make the outside water cooler and then have it mix, at the outlet. When it enters the pouch, the water mixes. And so the net temperature, that's one way we thought about doing it as well.
Your thermal epoxy, your paste, not necessarily a question, but sort of a comment. Make sure the off-gassing is appropriate. Make sure that the life of the paste is appropriate. Both of those things will bite you in the backside faster than a lot of other stuff.
Yeah, I can imagine. We haven't selected an actual type of TIM, but that when we were nailing it down, we would absolutely consider the material properties. I think because who knows what's in there.
Yeah, that trace contaminants build up pretty quick in an enclosed environment. Question on budget. I always hate asking these questions, but was the $9 million just to modify the current design, or is that for a current design built plus the cooling side?
So that's a great question.
Or is
because
it to just add cooling to the current? Yeah.
The way that we use the PCEC, not exactly how it likes to be used. So this was assuming ground up development. But that's why I included the ISS version as to show the increase, and that's roughly how much it would be in difference.
right? So like the current design is owned by taxpayers, all of us. So
Right.
you could go get that.
Exactly.
It's just adding on to that is the increase. Okay,
Yeah.
thanks.
Thank you.
I guess I'm out of questions, but I do have another comment that 316 does have pretty abysmal thermal conductivity.
Really
There
bad.
are other stainless steels or even other metals you guys could probably find that have the iodine compatibility that you want, but better thermal properties. So I suggest y'all look into playing with your material and playing with your geometry a little more.
I think we ended up selecting 316 due to like, we found that it was commonly
It's very
used.
available, yeah.
Yeah. So, but it's really, really bad thermal conductivity.
Yeah, it's basically an insulator.
Nothing else for me.
Same.
Did you look at, do you have any space concerns? So you're using 60 millimeter aerogel, which is, 4 inches, something like that. Are you insulating all your tubing, or is you just insulating certain areas? And if so, did you analyze the volume that'll take up in the enclosure?
We didn't analyze the volume, but it's just for the cold area of the Peltier side. So it'd be surrounding it'd be like just between the heat sink area and like the pipe itself. So it wouldn't be around the whole pipe per se. It would just be, probably likely have a thinner layer around the pipe itself, but most of the condensation will occur at the cold face of the Peltier itself, which is around 1.8 Celsius.
Okay, for this one, you might have addressed it already. So regarding the power, so whenever you need 421 watt of electricity, but you reject 800 watt, right? So it means if I want to heat up a cup of coffee, I need a lot of power for it.
So for the heat exchanger portion, we haven't quite spec'd out and figured out the exact amount of power it takes to draw that 380 watts away from the Peltier side. And then for the heating part, we're going to pick the ISS like heritage design, and we estimated that to be around 450 watts total, but that would not be running at the same time as the cooling side. Does that answer your question?
Yeah, kind of.
Sorry.
All right. Do we have any other additional questions from our judging panel? No? All right. We've got a little bit of time now to take questions from our live audience. Go ahead and raise your hand if you've got a question for the Cal Poly PHAT team.
Really great presentation, guys. I did have a question over, I know you guys are using 10 Peltiers. I know they're very inefficient. Do you know how efficient the overall system is?
Well, we have right here hold on, let's see. The overall system, well, it's all on the table right here. So for the worst case, which is a delta of 11 degrees Celsius, the COP is about 0.9. That's pretty high for Peltier standards, and it's only that high because we are running them at half the rated current. Because our assumption is we use 15 amp rated 180 watt Peltier coolers. And then as you can see for the best case, which is a delta T of about 2 Celsius, it's a COP of about 6.8 or 6.9.
Any other additional questions from our audience? All right, seeing no further questions, thank you so much, Cal Poly. If you've joined us on live stream this week, we want to thank you so much for being here for both days of presentations. This concludes our presentations and the live stream for the 2026 Human Lander Challenge Forum, but please check the HuLC website, hulk@nianet.org, to see our winners come this Friday. We'll also have a NASA feature story announcing the winners on Friday, so keep an eye out for that. Thank you so much for joining us, and we will see you next year.